तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
All right. So, we will resume our formal study of quantum mechanics by asking first if there are any questions, and then that will give us a starting point. Last time we discussed the uncertainty principle a little bit, and I tried to point out that quantum mechanics has some intrinsic, by its very nature, deep inside it there is a certain degree of uncertainty in our ability to completely understand or completely specify numerical values for physical observables. Now of course we must quantify this, and right away let me say that popular accounts on quantum mechanics very often tend to say that quantum mechanics is all about probabilities, and there is it is indeterminate and it is uncertain and so on and so forth. I should say immediately that only part of the statement is right. The rules for calculating probabilities are completely known, they are deterministic, there is nothing uncertain about that. But the fact is quantum mechanics does say that associated with physical measurable quantities you have a certain intrinsic statistical nature, which means that you can only talk in terms of probability distributions and all the other things associated with probability distributions like average values, mean square values, standard deviations and so on and so forth. So in that sense it differs from classical physics, classical Hamiltonian mechanics for instance, where we were able to specify the state of a system by a very precise point in phase space. The idea of a point in phase space is lost once you go to quantum mechanics, and that is the way things are. Okay. Now the framework in which you discuss quantum mechanics is mathematical, and in its most elementary form the mathematics is actually quite elementary. It is more elementary than what you need for say Hamiltonian mechanics, where you needed fairly sophisticated concepts such as Poisson brackets and symplectic structures and so on. In quantum mechanics this is replaced by a very linear kind of structure, the idea being that systems are specified, the states of systems are specified not by points in some phase space but by an element of a linear vector space, and this element is called the state of the system. It is an abstract concept, it is called the state of the system, and the idea is that there exists something called the state of a system which happens to be a member of a linear vector space, and this state of the system potentially can give you all the information you can find about the system. Just as in classical mechanics, once I tell you that a system has n degrees of freedom, you associate with it a 2n dimensional phase space, you find the generalized coordinates and momenta, and then a point in that phase space tells you the state of the system, specifying all the q's and p's tells you the state of the system. You have to throw that out in quantum mechanics. Okay. Now the experiments which led us to this kind of description are very long, and over the years they grew, and in the early days the interpretation of quantum mechanics posed a very severe problem. The formulation of quantum mechanics itself posed a fairly deep problem, but eventually things got ironed out, and by about 1926 or so the formalism was in place in some sense. Since that time many layers have been added to it, but the original foundational formalism that was initiated in a very remarkably short time in the early 1920s, that still remains in place. Okay. So let me start by saying that a system, a quantum mechanical system is described or specified by a state vector. I use the word vector because it is an element of a linear vector space, and the kind of symbols we would use for it changes from one book to another, one author to another, but by now there is a standard symbol for these states, and the one that I am going to use is called Dirac notation, and I will say a lot more about Dirac notation as we go along. It is denoted by something like that. I will use Greek letters for these state vectors, and I am going to put this mysterious angular bracket here just to tell you that it is an element of a linear vector space. Okay. Now whenever I say linear vector space, the way to imagine this linear vector space is to imagine a 3-dimensional Euclidean space, for example, and then of course you have vectors in 3-dimensional Euclidean space. 3-dimensional Euclidean space is a linear vector space, is one particular example, and therefore all the properties that we are going to talk about for state vectors, many of them can be imagined by thinking about ordinary 3-dimensional vectors and using vector algebra to add them. Now this state vector is actually a function of time, so that is the first thing you must appreciate. It is denoted by psi, and let me write it like this, psi of t, capital psi. I will use capital for the moment, you will see why I use a capital letter, because I want to use the small psi for something else, okay. And it is a function of time. To find out what happens to the state as time goes along, we have to prescribe a rule of evolution. Just as in classical physics, Hamiltonian dynamics, we prescribed Hamilton's equations of motion. In exactly the same way, I am going to prescribe a rule for this psi of t, and afterwards we will come back and simultaneously rather we will interpret what this psi of t is and how it gives you information on various quantities and so on. But first a little bit of a digression on linear vector spaces, and this is essential because many things I am going to say assume that you know about linear vector spaces or linear spaces. So let me go through a small mathematical digression on linear vector spaces. Now of course all of you have studied linear algebra. Is there anyone here who hasn't heard of a linear vector space or hasn't had linear algebra? Because if you have, then I can assume knowledge of this. How many of you have had a course in linear algebra? Almost everybody. 3 or 4 haven't, but have you had a course on matrices, for example? Everybody. So essentially if you know about matrices, you already know all the mathematics you need. So let me reassure you that there is not much left. All you need to know is how to handle matrices, and that too square matrices. Okay. Now let me formally define a linear vector space. I am not going to go through a lengthy exact description here. I might leave out a few things here and there, but we will fill them in as we go along. So this contains a set of elements which we call vectors. And I need a notation for these elements. So let us call this this notation psi, phi, chi, etc. I use Greek letters for these vectors, and these are called ket vectors for a reason which I will explain subsequently, but I use this funny angular bracket for it, because like tensor notation in ordinary tensor calculus, where we had the summation convention and the index notation, it was very convenient in that sense. In exactly the same way, this notation is a natural notation for quantum mechanics, so it helps you do calculations very easily once you use this notation. In fact, this is half the battle is won if you express things in the right notation, and this is exactly what the Dirac notation does. Okay. So it contains a set of elements between which you define certain operations, and the fundamental one is that of addition. So you say that you add two vectors so is linear vector spaces. It contains a set of elements which are elements of a linear vector space V. So it says that if psi plus phi, psi and phi are elements of V, this is also an element of V. So you add two vectors and you get another vector which also belongs to the same space. Moreover, this addition is associative in the sense that you could add psi plus phi plus chi, and this is the same as adding in any chi, and so on. It does not matter how you add vectors, you can add them in any order you like. Moreover, it is also true that this addition of course is commutative. You can add them in either order. Importantly, the linear vector space is a set of elements called vectors defined on a certain field, and this field is a field of scalars. So you also introduce simultaneously a set of numbers or scalars which belong to a field, and I do not want to get into what a field is right now. The real numbers form a field. You have addition, multiplication and so on and so forth defined in a field. The real numbers form a field, the complex numbers form a field, quaternions form, etc., etc. There are other examples, but I am not going to talk about general algebraic fields. The only fields we are going to worry about are real numbers and complex numbers maximum, and those quantities I will denote by A, B, C, etc. These are elements of some field. That field is generally the field of real numbers R or the field of complex numbers C, such that A psi is also an element of V. So you define multiplication by a scalar and it still gives you a vector. So you take a vector, you multiply by a scalar and you get a vector once again. Just like in ordinary 3-dimensional space, I have a position vector R, twice R or 3 times R, 2.5 times R is still a vector in exactly the same way. And this has all the obvious properties, namely A times B psi is the same as AB times psi. You can multiply all the scalars first and then multiply the vector, or you multiply one after the other. It's obvious they are all not going to make a difference. Now we are not going to worry at the moment about non-commutative fields, so we are going to assume real or complex. So this is R or C, and that is it. So that of course means that AB is the same as BA, it does not matter. Then the further properties are A times psi plus phi equal to A psi plus A phi. So all the obvious properties that you know about multiplying ordinary 3-dimensional vectors by real numbers, they are all listed one after the other. There exists in this space a special vector called a null vector, okay, such that I do not want to use 0 for that. So let me call the null vector 0. Let me write it in this form. Pardon me for writing it in this language because it is going to be a little confusing later on. We are going to use this for something else, but right now while we are talking about what a null vector is, let me just write null vector. The reason I am hesitant to write it in this form is obvious to you, is already known to you. When we solve some problems in quantum mechanics, we are going to look at some systems which have various states, and one of them is called the ground state. It would correspond to the lowest energy of the system, and occasionally I will use this symbol 0 inside the ket for the ground state, but that is not the null vector. So I should be careful when we do that, when we come to it, be careful. This null vector is such that any vector phi plus the null vector is still equal to phi. And among scalars, of course, there are two special scalars. There is a scalar which is 1, so 1 times phi is of course phi itself, okay. And 0 times phi is this. A null vector is a vector all of whose components are 0. The position vector at the origin, for example, is a null vector in 3-dimensional space. So since 0 times any vector phi is the null vector, sometimes what one does is forgets about writing the null vector, and one forgets about writing it like this and just uses ordinary 0 for the null vector because of this relationship. So you might as well just use ordinary 0 for the null vector, but you shouldn't get confused, because if I add two vectors I still get a vector. On the other hand, if I write vector phi plus vector psi equal to 0, what I mean on the right hand side is a null vector and not the scalar 0. But there should be no confusion, because it is obvious from this fact that I could as well just call this 0 and be done with it. Okay. So these are all the properties that you need, and of course since A runs over all scalars, say reals, all reals for example, you could have the idea of multiplying a vector by -1 and then you get minus the vector, etc. Now this set of properties defines a linear vector space, and there are lots and lots of examples of linear vector spaces all around. They have nothing to do with ordinary vectors in 3-dimensional space. These are abstract properties, and now you have many such examples, many examples of such vector spaces. For instance, the set of real numbers itself is a linear vector space. It is clear that the scalars would be the real numbers themselves, and the vectors would also be the real numbers, and you add two real numbers, you get another real number, and you have a null vector which is this number 0 itself, and so on. So R is a linear vector space. I call this LVS. The set of real numbers itself is a linear vector space. R2 points on a plane, a linear vector space, so Rn is also a linear vector space. In other words, the set of ordered n tuples x1, x2, x3 up to xn, such that I define addition by saying if you had two vectors with components x1, x2, x3 up to xn and y1, y2 up to yn, then the result vector is x1 plus y1, x2 plus y2 and so on. You add component wise, and that of course it forms itself forms a linear vector space. These are real linear vector spaces. When I go over to complex vector spaces, I would permit multiplication by complex numbers, for instance, and there are certain other properties that I would use. They would form a complex linear vector space, and these are the only two kinds of linear vector spaces we are going to look at. There are other instances which are not so trivial. For instance, the set of all n by n matrices forms a linear vector space, because you add two matrices, you get another matrix. There is a null matrix, you add things to it, nothing happens. You multiply the matrices by scalar numbers, real or complex numbers, you are still in an n by n matrix space, and so on. So the set of n by n matrices is a linear vector space. There are other even more non-trivial, non-obvious examples of linear vector spaces. For instance, the set of solutions of this equation d2x over dt2 plus omega squared x equal to 0. The set of solutions of this equation forms a linear vector space. Because it is a linear equation, there are primitive solutions to this, and of course those solutions would be x equal to, the solutions are e to the I omega t, e to the minus I omega t. They are the linearly independent solutions to this equation, and you can form linear combinations of them and they still continue to be solutions. A very popular linear combination of this is called the cosine of omega t, another is called the sine of omega t, but any a sine omega t plus b cos omega t is a solution also, and it satisfies all those axioms out there. So you see, linear vector spaces can be quite general. The elements could be numbers, could be vectors in ordinary space, could be vectors in n dimensional Euclidean space, could be set of matrices, could be a set of solutions of some differential equation, and so on. So the concept is very general and extremely useful. So far we have not introduced the idea, several ideas haven't been introduced. We haven't introduced the idea of a distance between two vectors. We haven't introduced the idea of the length of a vector. None of this has been done. We haven't introduced the idea of the product of two vectors, like a dot product or anything like that. Those are all add-ons which come later, but a linear vector space doesn't need any of those. A general linear vector space, that's it, this is it. But it's not very useful as it stands unless you put more structure to it, which is what we are going to start doing now. A very popular way of representing elements of Rn is to write them in the form x2 to xn, n real numbers, an ordered n tuple of real numbers. Okay. Now to perform manipulations with this, it is useful to represent this quantity in the following way. Write it as a column vector. That is one more way of representing an element of Rn. Okay. Now it immediately suggests to you, since you already know matrices, the moment you have a column vector, one is tempted to form a row vector and then multiply it on the left hand side to form a scalar. Okay. So the idea of the scalar product of two vectors emerges once you start putting this extra structure in, but it is not such a straightforward matter. We have to do this in general, allowing for all sorts of wild possibilities. So let us see how to go about that. Notice in particular I said we have not talked at all about the product of two vectors or the distance and so on. Just as Rn is a linear vector space, it is just the set of n tuples of real numbers. So an n tuple of real numbers of this kind, but we haven't endowed this Rn with a metric. We haven't said here is one element, here is another element, what is the distance between them. We haven't defined this quantity of distance. Once you put a metric, then this Rn becomes the Euclidean space En. Okay. We haven't done that yet. Okay. So the first thing we want to do is to try to see whether we could introduce the concept of a scalar product among these vectors. To do that, you need to recognize the following. Let me for the moment, just for a moment, and I will come back and correct myself, let me for the moment just drop this ket vector notation and write phi, psi, etc. as the elements of the linear vector space, just for simplicity. Then I would like to associate with each vector a scalar. So I choose a particular special member of this linear vector space, let us say phi, I choose this, and there are lots of elements in this linear vector space, chi, all sorts of things, could be a finite number, could be an infinite number, we do not care, it's sitting there. It is quite clear that when you allow for multiplication by real numbers, for example, you end up with an infinite number of vectors. It is immediately clear because I can the number of I can multiply by a real number between 0 and 1 and the infinite number of them, uncountably so. So I take a special element phi and I associate with each of the vectors in this space a scalar which I denote by phi psi. I denote it in this fashion. This is equal to some scalar which depends on that special element phi, and it is dependent on what is out there. I associate a scalar. I do not tell you at the moment how do I associate a scalar, we will come to that, but I associate a scalar. For every element of this vector space I have chosen a special element phi, and I do something with that element and phi, and I get a scalar number with a certain number of properties, and the properties are that phi a psi is the same as a times phi psi, phi psi plus chi equal to phi with psi plus phi with chi. So it says when you are doing this associating, if you take the sum of two vectors and you find the associated scalar, you might as well find the associated scalar for each of the members of the sum and add them up. Okay. By postulate I say that this is equal to that, and similarly if you multiply this psi by some scalar number, you might as well have found the scalar and then multiplied it outside. Okay. So the moment you put in these properties, then for every element here you can find such a scalar out there. Those objects, those scalars, the set of these scalars over all the phi's here, the size in this space, they form a linear space, they form a linear vector space. Really I should not say it is a function of psi, because this is not, it is a functional of psi, it depends on psi, but it is not some function in the sense of f of x or anything like that. It depends on this psi and it depends on your reference element phi. Now one can show that with these postulates this set of quantities forms a linear vector space itself, and you can, yes, pardon me. Well, a function I want to reserve for things where I can differentiate, integrate, continuity and so on. I do not want to use it. It is just a depends on this. I have a set of discrete elements, so it is clear that if it is a discrete set of elements, this is not a continuous function or anything, it just depends on this guy here. We will define functional more carefully later on. Okay. And it is a linear functional, and the whole idea is linearity, because this property, it is a linear functional. It does not depend on some squaring this or cubing this or taking logs or anything, it is just a linear function of this kind. And these fellows themselves form a linear vector space. And now you could say, why should I choose S phi? I choose something else. I choose another element and I compute the set of S chi of psi and so on. I choose all these guys. Well, all these linear vector spaces would form, all these guys put together form a linear vector space called the dual of V. So the set of linear functionals is an LVS. Dual. It is called the dual of the linear vector space. Okay. In other words, given a linear vector space, there is a natural mathematical way in which I can associate another linear vector space. So linear vector spaces come in pairs. The structure, these axioms have seen to it that they come in pairs of this kind. Yeah. Yeah, that's okay. Yeah, doesn't matter. It's still a linear vector space. Pardon me? The real numbers themselves form a linear vector space, as you know. The complex numbers form a linear vector space. Pardon me? For a fixed chi, but they are all isomorphic. So this thing, this set forms a linear vector space by itself.
So, but you haven't specified explicitly how the rule.
No, I haven't told you the rule at all. I am just saying associate. If you can associate with each psi a scalar by this, by some specified rule, we will come to that, then that forms a linear vector space. So as far as the existence of this dual is concerned, you do not need to know what is the actual rule. They have to satisfy these postulates, that is it. If
There may not be such thing for some.
there is, for every linear vector space you can define a dual. For every linear vector space you can define a dual. It may not be obvious, we have to know what is the rule, how do you go about it, etc., such that these are satisfied, okay. But there is a dual to every linear vector space. Pardon me?
Why it is dual, that name dual?
Why is it called the dual? It is like the twin. It is like the twin. Here is a vector space and here is a companion. So the dual, if you would like to call it a mate, that is fine, or you like to call it a companion, that is fine, but dual is the mathematical term used for it. Okay. Yeah.
Can we get back V from the dual?
That's a very good question. Can I reconstruct V from this dual? We will answer this, we will see. By looking at examples we will see how you can try to get back V. Yes. Yes.
Each element itself a vector space.
Pardon me?
Isn't each element of the vector space itself a vector space?
What do you mean by each element is a vector space?
Isn't S phi itself a vector space? That function.
This alone is a vector space, yes. But there is no guarantee that, you see, for a linear vector space, this is like asking, is a given element of a linear vector space a vector space? No, of course not, because you end up with, that is not true, because you may not have the null element, you may not have the other properties and so on. So it is the collection we always talk about. Let me write down what this is for Rn, and then immediately you will see what this quantity is. Yeah.
So we can have more than two rules to get the S phi of psi.
There is a unique dual to every linear vector space. Okay. For every linear vector space there is a unique dual. I am not proving all these theorems, I am not stating in its greatest generality and most rigorous form, because my idea is to show you the operational method. But what are you going to do for Rn, for instance? Okay. So these are all theorems which exist, which can be proven. There exists a unique dual for every linear vector space. Now the question is, what is the use of this? That is the important thing. What is the use of this linear vector? The use is, let me say it in my own way, which is not perhaps the most rigorous way. There is a natural way to associate a scalar with a vector. As you know, in ordinary 3-dimensional vector spaces, in ordinary 3-dimensional vectors, if you are given vectors like A, B, C, etc., and asked to construct a scalar from these vectors, you do something called a dot product. So this quantity here, this thing here is the dot product. So we are heading towards a dot product of two vectors by associating a scalar with a pair of vectors. So it is a bilinear operation. Notice that I am taking two vectors and doing something to it to get a scalar. The idea is you get a scalar. That is the general way of doing this. Now if you looked at now, since these S chi's etc. themselves form a linear vector space, it is convenient to say that this vector space here, which consists of a set of elements here, is represented by writing this psi in this form. This is an element of V, and by saying that this phi here on the left hand side in this bracket, let me write it in this form and say that this is also a vector, a different kind of vector which lives in the dual space. Okay. In other words, what I have done is a sleight of hand. I have a set of scalars, and now I am saying for every number which is in this space, in this set, the whole set of numbers, they are all created by taking the original ket vectors elements of V, doing something to that using this reference element phi. So this set of numbers I write in a given notation. Instead of this kind of bracket, I use this notation here, and I say this is an element of the dual space. These are called bra vectors, these are called ket vectors, and instead of phi psi I replace it by this notation phi psi. Okay. Entirely a matter of notation, so that I do not have to go on writing a subscript phi here, put a comma here and so on. This is inconvenient. This is the notation used in mathematics, this is the notation used in physics. So what you have done is to take the set of linear functionals here and replace them by an element of a dual space phi, and then you say this quantity here stands for the linear functional, stands for this scalar. So the dual vectors are going to be written in a different form from the ket vectors from V, so that I know that these belong to V tilde rather than V. Okay.
So the dependence on psi is ignored in that notation.
Where is it ignored?
So in the bra vector notation,
Yeah,
we have written only phi.
exactly. So how do I construct all the elements? I take all the elements of the original. Okay, his confusion is the following. This involves chi, this involves phi, they could involve many other vectors. All those vectors, all these guys I now say are represented by this phi here, with chi, phi for every element in the original vector space. There is a corresponding element in the dual vector space here, such that I take one element from the dual space, I take one element from the original space, and I form a bilinear combination to give me a scalar which satisfies these properties. Okay. Now so immediately I should give you an example, and then you will see at once how this happens. If in Rn so I write x1, x2, x3, xn is an element of Rn. If I construct the corresponding row vector in this form, then I say all the row vectors are elements of the dual to Rn, the original column vectors are the elements of Rn itself, the original vector. Then there is a natural way to produce a scalar which satisfies these properties, which is matrix multiplication with the bra vector on the left and the ket vector on the right, or the row vector on the left, the ket vector on the right, the column vector on the right. So it is immediately clear that x1, x2, x3, xn with say y1 to yn, this is a scalar, it is x1 y1 plus etc. up to xn y. I multiply this by a scalar number, the whole thing is multiplied, each element is multiplied, the answer is multiplied by a scalar. I add two of these guys, y to y1 to yn, z1 to zn, and I multiply on the left, I get the addition. Usual rule.
The dimensions of dual space and
the dimension, yeah, now we haven't said what a dimension of a space is, but it is intuitively clear that the dimension of the space must be the same as the dimension of the original space. It is clear that since I have said that it is in one-to-one correspondence, for every element in the original vector space there is a conjugate, there is a corresponding adjoint element in the vector, there is an element in the dual vector space. Okay. And the way to remember it is to say that one of them is represented by column vectors, the other by row vectors. I could have changed this notation. I could have said the original space is represented by row vectors and the other by column vectors. It would make multiplication a nuisance. You would have to be careful how you multiply. Since I multiply row by column, that is the rule for matrices, that is the way we have stuck. So we will use this convention. Yeah.
So you said that there is an arbitrary reference phi.
Yeah.
Abstract. Can you
Yeah.
say what are the reference here? Is it an
No, I am saying that you have to exhaust all members of the original set here too, and that forms a dual space. So the set of linear functionals has now been replaced by the set of bra vectors. Okay. And here is the rule for finding these scalars. This may not be always the rule. Now for example, I told you there are solutions of differential equations which form a linear vector space. The question is, what do you mean by adjoint? What do you mean by the dual space here? How do you define this these linear functionals? We will come to that. The further complication, if you like, in some sense is it's not a complication, it's a simplification, but it looks a little confusing, is that this space here is actually exactly the same as the original space itself. So it so happens that Rn is the same as its dual. There is a one-to-one correspondence, it is completely the same as its dual, it is self-dual. That can happen sometimes, but still we would like to distinguish between the space and its dual, and therefore I will represent one of them by column vectors and the other by row vectors. But you could ask, what is wrong with representing a point in n dimensional space either by a column vector or by a row vector? It makes no difference at all, it is exactly the same thing, but I would like to distinguish between the two, even in cases where Rn happens to be the same as even in such cases I would still do it. Okay. It should be sort of becoming obvious to you that finite dimensional linear vector spaces are more or less like n dimensional Euclidean space itself. In fact, there is an exact theorem which says that every n dimensional, I will define a dimensionality of the space, every n dimensional linear vector space is isomorphic to n dimensional Euclidean space. In other words, you can think of every n dimensional vector space in terms of column vectors and the corresponding row vectors. Okay. It is only when you go to infinite dimensional spaces that you run into some technicalities which are non-trivial, but all finite dimensional spaces look exactly the same.
But in this case, we have defined a binary operation, say an operation.
Yeah.
The first element in the binary operation, the first element is from one linear vector space.
That's right.
The other element is from another vector.
That's right. That's right.
But intuitively, we have to define an operation that operate two vectors in the same vector space.
No, that is the beautiful point. You cannot define the multiplication of two vectors, both of which belong to the same vector space. So every time you take a dot product of two vectors in ordinary 3-dimensional Euclidean space, you are really taking one element from the dual space, one element from the original vector space, and taking the dot product. As you can see, you cannot multiply two column vectors, right, and get a scalar. To get a scalar, you need to have a row on the left and a column on the right. Okay. It is just that in ordinary 3-dimensional space, these two are the same space. So one does not realize that one is doing this. But if you were to write it out in terms of column vectors and row vectors, it is quite clear that you form a scalar or take A dot B, the way you write A dot B as A1 B1 plus A2 B2 plus A3 B3. If you represent A and B by column vectors, the A on the left hand side has to be a row vector. Okay. So that is an important point. A scalar product between these vectors is only defined by taking one element from V tilde and one element from V. In 3-dimensional Euclidean space or in n-dimensional Euclidean space, which is self-dual, this distinction is lost, but is tacitly there, okay, which comes out when you represent these vectors in terms of column vectors and row vectors.
Is that what happening? We define an inner product in water space.
Yes, you always define an inner product always by taking elements from the dual and the original space, always. Okay. And it will become particularly important when you look at infinite dimensional spaces. Then you have to be very careful that you do just that. Okay. You can define a product of a vector with itself, but then it is a map to something else. You can define you can define a V direct product with V. So I would take a given vector and I take another vector from the same space, and this would be a map from the original vector space to a copy, a direct product of this space. So that is a different space altogether, its dimensionality is higher. If each of these is n dimensional, then the dimensionality of the other space is n squared. Okay. And of course if you take ordinary Cartesian vectors with components like a, b, c, etc., a vector, b vector, and I write components, then the set of numbers a, I, b, j is precisely this. It is an element of V cross V, because you see if I take A equal to A1, A2, A3, and I consider this set of numbers AI, Bj, there are 9 possibilities here, right. So immediately you see that this quantity, this combination AI, Bj is not an element of the original R3, it is an element of R3 cross R3, it is a 9 dimensional space. Okay. And this kind of thing, how would you write it? Well, I would write it like this. I simply write it like this for want of a better notation, without a dot, without a cross, and it is a tensor product. So you can take a vector space and multiply it by itself, direct product any number of times, and form higher dimensional spaces, okay. And they are called Cartesian products or tensor products. But we are not talking about that, we are talking about finding a scalar from these vectors. And for a scalar you take an element of the dual, you take an element of the original space and you multiply. Okay. Now the moment I do this, I also have the possibility of defining the inner product. I call this number the inner product, I call this this thing here psi phi scalar product or inner product. And it has the properties we wrote down for S. The moment I do this, I can define the inner product of a vector with itself. Okay. In particular, I could define this. Now what would this kind of thing be? In ordinary 3-dimensional Euclidean space or n-dimensional Euclidean space, what would this be if psi is represented by x1, x2 up to xn? Then this quantity here is equal to summation I equal to 1 to n xi squared, and you would say, this corresponds to the length of this square of the length of this vector. So if I say it is a vector in n-dimensional space with components x1 to xn, the sum of the squares of the elements is the square of the length of this vector, and because it is a sum of real number positive quantities, it would be 0 only if and only if the vector is a null vector. So this is equal to 0 if and only if psi is the null vector. Okay. We would like to preserve this property. We would like to say that the square of the length of a vector, length in general in n-dimensional vectors, in arbitrary vector spaces, a vector has 0 length if and only if it is a null vector. We would like to preserve this property, but then we have said that these vectors are completely general quantities and could in fact be multiplied by complex numbers. Then this is no longer true. How would you preserve that? How would you make sure? I take the complex conjugate here and define the element in the dual space by taking the complex conjugate. So if these fellows are not elements of Rn but are elements of a general n-dimensional vector space, so to avoid confusion let me use some other symbol for it, let us call it alpha 1 to alpha n, then if this corresponds to psi, this guy psi should really be alpha 1 star, alpha 2 star, alpha n star. Okay. And then we are in good shape because this corresponds to now mod alpha I whole squared, and you are guaranteed that it is 0 if and only if each of the alpha i's is 0. Okay. So we begin to see our first generalization, that if you are looking at complex vector spaces, the thing to do is, if you have an n dimensional vector space, the elements are written as row vector, column vectors. In the dual space, the bra vectors are the complex conjugate transposes. So this is the reason why in matrix analysis complex conjugation is not a very natural operation. Complex conjugate transpose is a natural operation always. Finding the complex conjugate of a matrix does not do anything very interesting, but finding its complex conjugate transpose does so always, and that is called the Hermitian conjugate, okay, when you take complex conjugate transpose. So this relation is still true, but it also implies that this is true. If you have a vector A on psi and this is equal to psi prime, say, then what is psi prime? What is the corresponding psi prime? You have to take each element of psi, write it as a column vector, multiply by A and take complex conjugate transpose. So it is immediately clear that this is equal to A star on psi. So any scalar you multiply by, if it is multiplying an element of the dual space, you start with an original vector, multiply by a scalar, you get a new vector. If you want to find its adjoint in the dual space, then take the adjoint of the original vector and multiply by the complex conjugate of the number of the scalar. Okay. And of course this will satisfy all those associative properties and so on and so forth. But this is a crucial property. Okay. Moment of you have this, you can now start defining the distance between two vectors, okay, because you have the idea of a scalar product. Incidentally, notice that this rule also implies that phi with psi, which is a scalar, if I take the complex conjugate of this scalar, this is equal to psi with phi. So scalar products in general do not have to be real, it could be complex numbers, but the scalar product, the inner product of phi with psi is not the same as the inner product of psi with phi, because there is a complex conjugation involved here, okay. That is missing in real vector spaces, and that is why you write A dot B equal to B dot A. That is not true in general. A dot B is B star dot A always, but in a real vector space you are multiplying only by real numbers, this complex conjugation does not make a difference. Okay. Okay. And now we would like to ask, I would like to define the norm of a vector. And I denote it like this. This is defined, this is the definition, as psi with psi to the power half, the positive square root of this positive number, this non-negative number. Okay. And of course it is equal to if and only if psi is the null vector. Okay. Now we are going through things which are exactly the same as what happens in ordinary 3-dimensional Euclidean space, and those concepts should remain when you generalize this system. And therefore one would like to have a statement like psi plus phi here, this quantity, the norm of the length of the sum of two vectors. Now this obeys a triangle inequality. You know, in ordinary 3-dimensional space the sum of two sides of a triangle is greater than the third always, unless the triangle collapses, it becomes collinear. So this quantity is greater than or equal to psi plus phi. Pardon me? Oh, I am sorry. I have created new mathematics by getting rid of inverting this inequality. Yeah. It is the famous triangle inequality. Okay. But you also know another thing. You also know that if you took ordinary vectors, I took a vector A and I dotted it with B in R3 in the usual real vector space, this quantity is AB cos theta, right, by definition, where theta is the angle between them, and the magnitude of cos theta is between -1 and +1. It is equal to +1 if the angle is 0 and -1 if the angle is pi, and that is the extent to which it can vary. Therefore it follows that the norm of the magnitude of A dot B is less than or equal to the magnitude of A times the magnitude of B. Right? That is just a statement that the cosine has a value between -1 and 1. Now that is generalized to this general vector space, and the statement is that phi with psi mod squared, because it is a complex number in general, so you need mod squared, is less than or equal to the norm of phi, but let us write it out, phi with phi, psi with psi. The question is now, when is it equal? Just as in ordinary geometry, by the way this has a name, this is called the Cauchy-Schwarz inequality. It is crucial, we will use it very extensively. For instance, we will use it to establish the uncertainty principle. It is really a statement from here, and the uncertainty principle itself will be generalized, but really it follows at the mathematical level, it follows from the Cauchy-Schwarz inequality. Now this inequality, you could ask, when is this guy an equality? Only when A and B are in the same direction or antiparallel. In other words, they are collinear. The same thing is true here. And what does it mean to say that two vectors are collinear? It means one of them is a scalar multiple of the other, the direction is the same. In exactly the same way, this thing becomes an equality if and only if phi, for instance, the ket vector phi, is in the same direction as the ket vector psi. In other words, it is just psi multiplied by a number. What would you say to that? So this equality, if and only if phi equal to some A times psi. What does this mean? Linearly dependent. Only if and only if phi is linearly dependent on psi. Psi itself could be made up of adding several vectors. Every vector can be decomposed into other vectors. So if phi is linearly dependent on psi, then the Cauchy-Schwarz inequality becomes an equality, but otherwise it remains always strictly less than, this quantity always remains less than this. We will see how powerful this statement is, an incredibly powerful statement, because we can prove all kinds of things with it. Just to give you an example from way out from this whole thing, you know, you take the gas in this room, it obeys a Maxwellian distribution of velocities, and you can compute the average speed. So let us compute, for instance, the average speed, and let us call it V. I compute this quantity V, and this depends on the square root of the temperature. It is some root kT over m, where m is the molecular mass, k is Boltzmann's constant, multiplied by some number 8 pi 3 whatever it is. You could also ask, what about 1 over V, what about the average value of the reciprocal of this velocity, of the speed, and it is clear that 1 over the average is not the same as the average of 1 over the speed. The reciprocal of the average speed is not the same as the average of the reciprocal, it is not the same as taking the average value, you know what I mean, this is not in general equal to that, but you can show but you can show this is greater than or equal to 1, and in fact in this case it is strictly greater than 1. This can be shown very trivially by using the Cauchy-Schwarz inequality. So one line proof. We will do that at some stage. So just to show you that this inequality, which starts off very innocuously with just the scalar product of two vectors in ordinary space, has profound implications. It is part of a much deeper thing. In fact, you can generalize this to the set of this is two vectors at a time. You could ask, is there a similar thing, n vectors at a time, an arbitrary number of vectors at a time in the space, and yes, we will see that there is such a thing too, there is such a relation too. So that is a statement of whether these vectors are linearly dependent or linearly independent. Okay. That brings us to the concept of linear dependence, which will then bring us to the concept of basis set in this vector space, expansions and basis sets, orthogonalization and so on. We will talk about that next time.